Okay, so I got a 30-pound flywheel A, radius of gyration 4 inches. I've got a disc 50 pounds, coupled by a belt as shown here. Uh, Apply a moment of 50 times the time, where time is in seconds. I want to find how much time it takes to get that disc to start spinning at 60 radians per second starting from rest. So again, I'm trying to find a velocity at a specific time, so I'm going to use impulse momentum on this guy. Okay, so we'll start by drawing some free body diagrams. So I got this guy here with a moment of 50t on it. I got a bunch of stuff going on here. It's not really going to matter, so I'm not going to label them, but I've got pin joint, all that good stuff. Okay, but what is more important is I've got a tension here and a tension here, and it's a different tension. If it was the same tension, I wouldn't have any spinning, so I've got to have that tension going on there like that. Okay, now if I look at the disc, a little bit larger like this, it's got the same tensions, just in opposite directions. Okay, and those are the only forces acting on this guy. Again, I've got pin joint, weight. I'm not going to label those because I'm going to do angular momentum on this stuff because I don't have any linear motion, so it's not really going to be of any help to me. And I'll do that about the center there where all those forces will go away. Okay, so again, my equation that I'm going to use is I omega 1 plus the sum of all of my angular impulses. Now this time, those change with time, so I'm going to leave the integral right in there, unlike if we have a constant thing here. So again, these guys are both starting at rest. So basically I have an applied moment and a final angular velocity. So we'll go ahead and start with disk A, which is going to have the moment of 50t dt. And again, this is going to go from 0 to some time that I'm trying to find, right? Then I'm going to have two tensions, right? I'm going to have a positive T2, right? Times the distance, which is I'm going to do everything in feet, so that's going to be a half a foot. So that's going to be plus 0.5. I should do the integral. 0.5 times T2, which again changes with time, so I've got to leave it inside the integral dt. Then I've got a negative T1, so it's going to be negative 0.5 T1 dt. And again, that's going to equal I times omega 2. Now, I for this A is just going to be its mass. So 30 divided by 32.2 times the radius of gyration, which is 4. But I want that in feet, so I'm going to divide it by 12 squared times omega 2. Let's take 2 seconds and find the omega, because again, I want to know, omega b, I want to be 60, right? So in order to find what omega A is going to be when omega B equals 60, I'm going to say, okay, 6 times omega A equals 9 times, well, not omega B, well, yes, omega B, which is equal to 60. From that, I can find that omega A is going to be 90. Okay, so omega A rotates at 90 radians per second to get omega B to rotate at 60 radians per second. So this is going to be times 90. All right. So I've got time in there. I've got some tensions. I don't want to deal with those. We'll do the same thing for the disk. Now in this one, T1 is positive. So, and it's going to be, instead of 0.5, it's going to be 9/12, which is 0.75. So it's going to be the integral of 0.75 T1, that one's the positive this time, dt, minus the integral, oops, I forgot the 0.75, 0.75 T2 dt. Now there is no applied moment on this one, it's just those tensions, and that is going to equal I omega 2. This time I is for a disk, which is 1/2 mr squared. So it's going to be 1/2. This one doesn't weigh 30, it weighs 50. Divided by 32.2 times r squared, which is the 0.75. And then this guy is times 60. So again, that's I of a disk, 1/2 mr squared. Its rotation is 6. Now, what I can do here is let me kind of rearrange each equation, clean them up a little bit. That top equation, I can do that integral of the 50t, and I'm just going to go down to 25t squared. Okay, that's the integral of 50t. Okay, and then what I'm going to do is I'm going to lump together the t2 and the t1 like so. I'm going to have the radius of 0.5 times the integral of t2 minus t1 dt. And then that is going to equal, I wish I had it here, but I don't, so I'll just leave what I have on the right side. 30 divided by 32.2 times 4/12 squared times 9. That's just some number. I don't have the number right in front of me, right? So I've got that guy. Then the second equation, I can rearrange a little bit, and I get negative 0.75 times the integral of t2 minus t1 dt. Okay, and again, I put that negative sign in there to get it to look the same as it does above. Okay, and that's going to then equal, again, I don't have all of that, but it's going to be the 1/2 times 50 divided by 32.2 times 0.75 squared times 60. And what I've got here is effectively I can solve for this guy and then plug it in up there. Okay, so I just solve for that whole integral. I'm not actually finding I'm not finding the tensions or the equations for the tensions, but I know that the impulse of those tension, the difference between them, I can find from the bottom equation, plug it into the top equation, and then I just have a single equation that I can solve for t with, and I get t equal to 1.06 seconds. Excuse me, this is actually 1.04 seconds. Messed that up right there. But again, do impulse momentum on each of these disks essentially. Okay, you have to use the tensions in the belt. However, you don't have to solve for them directly. You just have to solve for the impulse that they create, and then use the difference in those impulse to go ahead and solve for the time.